Welcome to the Deep Dive. We take sources you're interested in, explore them, and help you get up to speed quickly.
That's the plan.
And today, it's all about artificial intelligence. Its history, where we are now. We've got quite a mix of sources.
Yeah, some Wikipedia articles, AI winter, artificial intelligence, that Whip a white piece. Avicenna on history, EDI Weekly on AI types, Tech Target. A good spread.
Right. So the mission is to pull out the really important stuff. Understand the journey AI has been on.
Yeah,
It's been a bit of a roller coaster.
as putting it mildly. It started pretty early, actually, spurred on by the Cold War.
Oh, yeah.
Yeah, back in 1954, the U.S. government, even the CIA, got really interested in machine translation for Russian documents, obviously.
Makes sense. Strategic advantage.
Exactly. They thought it was bigger than just intelligence, though, a broader potential.
So that initial push, that led to some of the first actual AI work, like neural nets.
Precisely. You had Pitts and McCulloch, Minsky's S-Narch machine. This is the late 50s. Early attempts at, thinking machines.
But it wasn't smooth sailing, was it? These early neural nets, they hit limits.
They did. I mean, the ideas were there, but the tech wasn't quite ready. They couldn't really deliver on the big promises. So researchers kind of pivoted. They moved towards symbolic AI, focusing more on logic, rules, manipulating symbols. That seemed more achievable at the time.
And then there was the whole perceptron thing. That initially looked promising.
Very promising. Frank Rosenblatt was a big champion. But then Minsky and Papert wrote that book in '69.
Perceptrons, yeah.
Right. And it basically laid out the mathematical limitations of the single-layer perceptrons they had then.
So did people just not know how to make them more complex?
Essentially, yes. They didn't have the methods yet to train multi-layered networks effectively, things like backpropagation that came later. So without a clear path forward, the enthusiasm just cooled off. Funding dried up for that line of research.
This wasn't just happening in the U.S., right? You mentioned the U.K.
Right, the Lighthill Report in '73. That had a huge impact over there.
Wasn't there some famous debate tied to that?
Yeah, a BBC debate basically asking if the whole idea of a general-purpose robot was just a mirage.
Wow, pretty blunt.
It was. The report itself pointed to really fundamental problems, especially this thing called the combinatorial explosion.
Okay, what's that exactly?
Imagine trying to plan something and every choice you consider branches out into tons more possibilities, and those branch out.
Yeah.
It quickly becomes computationally impossible to explore everything. It's a massive hurdle for complex reasoning.
I see. So the number of possibilities just explodes.
Exactly. And the Lighthill report basically said AI hadn't cracked these fundamental issues, leading to big funding cuts for AI research in the UK. Only a few universities kept going.
A real AI winter, then.
The first one, yeah. Though, interestingly, the UK did jump back in later,
Oh, when was that?
around 1983, with something called the ALVI project.
What prompted that comeback?
It was mostly a reaction to Japan's big fifth-generation computer project, which had a strong AI focus. The UK felt they needed to compete.
International competition driving research.
Yep. But even the ALVI project ran into funding problems eventually.
Yeah.
Sustaining that long-term AI vision is tough.
Okay, so after that first winter, things picked up again in the 80s.
They did, yeah.
Yeah.
Big time, actually. This time, the buzz was around expert systems.
Expert systems. What were they?
They were AI programs designed to mimic the decision-making of a human expert, but in a very narrow field, like configuring computer systems.
Okay, so very specific tasks.
Very specific. The classic example is XCON, used by Digital Equipment Corporation, or DEC. It configured their VX computer systems.
And was it successful?
Hugely. Reports say it saved DEC something like $40 million over about 6 years.
Wow, okay, that's real money. I can see why businesses got excited.
Absolutely. That kind of tangible ROI fueled massive investment. By 1985, companies were pouring over $1 billion into AI.
$1 billion in the mid-80s.
Yep, and a whole industry popped up around it. Software companies like Knowledge, IntelliCorp, and even specialized hardware companies. Symbolics, LISP Machines, Inc. They built computers specifically designed to run LISP.
LASP machines. Dedicated AI hardware.
That's right. LISP was the favored language for a lot of AI work in the U.S. back then. Felt like a golden age for what?
But I sense another but coming. This didn't last either.
It didn't. The market for those specialized LISP machines started collapsing around 1987.
Why? What happened?
A couple of things. Cheaper, more general-purpose computers like workstations from Sun and Apollo started getting powerful enough to run LISP effectively. So the need for specialized, expensive hardware faded.
Technology leapfrogged itself.
Kind of, yeah. Plus, maybe the expert systems themselves were a bit overhyped, or at least the difficulty of building and maintaining them was underestimated. The knowledge acquisition part was still really hard.
So the second AI winter.
That's what they call it. Another period where funding got tight and the hype died down considerably. It seemed like AI just couldn't quite live up to the expectations.
Okay, so two winters. That brings us more towards the present.
Mm-hmm.
We hear about an AI spring or AI boom now, starting around what, 2020-ish?
Yeah, roughly the last few years.
Hmm.
And this time, it feels different. The scale is just enormous.
How so?
Look at the numbers. Publications, patents, they're way up. Investment hit something like $50 billion in 2022 alone.
50 billion.
And jobs. Around 800,000 AI-related job openings in the U.S. in 2022. It's unprecedented.
Okay, those are staggering numbers. What's driving this boom? What successes are making the difference this time?
What you're seeing, real-world applications that work incredibly well. Think about language translation. Google Translate is pretty amazing now compared to even a decade ago.
True.
Image recognition, too. ImageNet spurred massive progress, and now it powers things like Google Image Search. And then there are the game-playing AIs.
Right, like AlphaGo beating the World Go champion. That felt huge.
It was huge for public perception, definitely. Showed AI could handle complex strategy. And IBM's Watson winning Jeopardy before that. AlphaZero learning multiple games.
So tangible, high-profile wins.
Exactly. But within the research community, a really key moment was probably 2012.
What happened in 2012?
The deep learning system, called AlexNet, absolutely crushed the competition in the ImageNet challenge. It used deep neural networks, and its performance was so much better than previous methods. It really signaled that deep learning was the way forward for certain kinds of problems, especially perception.
AlexNet. Okay, so deep learning really kicked things into high gear.
It was a major catalyst for the current wave, yes.
So looking back at these cycles, ups and downs, are there underlying challenges in AI that maybe explain why progress wasn't always smooth?
Definitely. That combinatorial explosion problem we mentioned earlier, still a thing.
Still hard to just explore every possibility.
For really complex reasoning tasks, yes. It just scales incredibly badly. It's interesting because humans often use intuition, sort of gut feelings, not step-by-step logic for everything. Replicating that intuitive leap is still really hard for AI.
Right, we don't calculate every single chess move possibility.
Exactly.
Yeah.
Another huge challenge is knowledge representation. How do you get an AI to actually understand the world?
You mentioned ontologies.
Yeah, ontologies help structure knowledge, define concepts and relationships. Think of them like super detailed maps of how ideas connect. They're vital for things like intelligent search or question answering. It helps the AI know that, say, a dog is a type of mammal, which is a type of animal.
So building a structured knowledge base.
Right. But the really hard part is common sense knowledge.
What do you mean?
All the stuff an average person just knows about the world. That water is wet, you can't push on a rope, if you drop something, it falls. It's vast. And a lot of it is sub-symbolic, hard to write down as neat rules.
Ah, the unwritten rules of reality.
Pretty much. And then there's the knowledge acquisition bottleneck. How do you even get all that knowledge into the AI system efficiently? It's a massive ongoing challenge.
Okay, that makes sense. What about decision making? How do AIs plan or decide what to do?
Well, in AI terms, you have an agent, something that perceives its environment and acts. Planning usually involves finding a sequence of actions to reach a goal. Decision-making often brings in utility, trying to maximize some value or preference.
So making the best choice according to some metric.
Exactly. But traditional planning often assumed a predictable world. Real-world AI needs to handle uncertainty, things not going exactly as planned. That requires probabilistic reasoning, adapting on the fly.
Like us, basically. We don't know everything that's going to happen.
Precisely. And the way AI learns to do this is also key. We talked about deep learning, but there's also reinforcement learning.
Learning by trial and error, getting rewards.
Kind of, yeah. Rewarding good outcomes, penalizing bad ones, so the AI figures out the best strategies over time. Think about training a dog, but for algorithms.
Okay. And transfer learning.
That's about leveraging knowledge from one task to help learn another related task faster. Don't start from scratch every time.
Efficient. And deep learning is the one using those neural networks.
Yes. Inspired by brain structure, often with many layers. It's particularly good at finding complex patterns in large data sets. And there's a whole field, computational learning theory, that studies the math behind how and why these learning methods work.
Got it. Now, within deep learning, especially for language, you mentioned transformers.
Right. Transformers have been revolutionary for natural language processing NLP. They use something called an attention mechanism.
Attention, like paying attention.
Sort of, yeah. It allows the model to weigh the importance of different parts of the input data, like focusing on the keywords in a sentence to understand its meaning. This, along with techniques like word embeddings representing words as vectors, led to these powerful GPT models.
Generative pre-trained transformers, they're everywhere now.
They are. They generate text that often feels remarkably human.
But even with all this progress, there are still areas where AI struggles. Perception, you said.
Yeah, things like computer vision or speech recognition, tasks that seem effortless for us, recognizing a face in a crowd, understanding mumbled speech, can still be tricky for AI, despite huge improvements. It's Moravec's paradox again.
Moravec's paradox.
The idea that things humans find hard, like calculation or logic, are relatively easy for AI, while things we find easy, like perception and mobility, are incredibly hard for AI.
Interesting. So when AI is solving problems and it can't just brute force it because of that combinatorial explosion, what search strategies does it use?
It uses smarter approaches. Heuristics, basically rules of thumb, to guide the search towards promising solutions faster.
Shortcuts.
Educated shortcuts, yeah. Then there's adversarial search for games where it plans moves considering the opponent.
Like chess AI.
Exactly. And things like evolutionary computation, which uses ideas from biology like mutation and selection to evolve better solutions over generations, or swarm intelligence, inspired by ants or birds finding efficient paths together.
Wow. Inspiration from everywhere. Nature. Games. What about more traditional logic? Does that still play a role?
It does. Formal logic, propositional logic, predicate logic is still important for representing knowledge precisely and performing rigorous reasoning. But it often struggles with uncertainty,
Right, the messy real world.
which is where probabilistic methods come in. Things like Bayesian networks allow AI to reason and make predictions, even with incomplete or noisy information. They deal in likelihoods, not just true-false.
So logic for structure, probability for uncertainty.
That's a good way to put it.
Yeah.
And then you have classifiers, statistical learning methods.
Classifiers, like sorting things into categories.
Exactly. They learn from labeled data examples where you know the correct category to predict the category for new, unseen data.
Examples.
Things like decision trees, which use a series of branching rules. K-nearest neighbor, which finds the closest known examples. Support vector machines, SVMs, naive Bayes. Lots of different statistical techniques to draw boundaries between categories. Deep neural networks are also very powerful classifiers.
Okay, let's circle back to the GPT models, since they're so prominent. How do they actually generate text? It seems magical sometimes.
It's statistically driven, really. They predict the next token could be a word, part of a word, punctuation, based on the sequence of tokens that came before it.
Based on what they read during training.
Exactly. They're pre-trained on absolutely massive amounts of text from the internet, books, etc. They learn the statistical patterns of language grammar, facts, reasoning styles, even biases, all from that data.
So it's pattern matching on a colossal scale.
The very sophisticated form of pattern matching, yes. Then they're often fine-tuned.
Fine-tuned.
That means further training on a smaller, more specific data set to make them better at particular tasks, like answering questions or following instructions. Sometimes this involves reinforcement learning from human feedback, or RLHF, to align their outputs more closely with what humans prefer.
RLHF getting human feedback to steer them.
Right. But even with all this, they have limitations. They're known to hallucinate.
Hallucinate, like make things up.
Essentially, yes. They might generate plausible sounding but factually incorrect or nonsensical information because they're fundamentally predicting likely sequences, not accessing a knowledge base of truth.
Ah, so they can sound confident even when wrong.
Very confident.
Yeah.
Though there's interesting work using LLMs in areas like mathematics, trying to improve their reasoning, using techniques like supervised fine-tuning on math problems, prompting them to show reasoning steps. Companies like Alibaba and Microsoft are developing specialized math models.
Okay, so powerful but flawed. That actually leads nicely into the whole topic of risks and ethics with AI. It's not all just amazing progress, is it?
Far from it. There are significant concerns. Privacy is a big one.
Because they need so much data for training.
Exactly. Machine learning, especially deep learning, thrives on vast data sets. Where does that data come from? Often from user interactions, online activities. Think about smart devices, online services. They collect enormous amounts of data.
And the companies controlling that data.
Tend to be the big tech players, yeah. They have the cloud infrastructure, the computing power, and the data streams. That concentration of power is itself a concern. Balancing the utility of AI services with individual privacy is a huge challenge. And then there are copyright issues with the training data too.
Right. What else?
Environmental impact. Training these massive models, running the data centers, it consumes enormous amounts of electricity.
I've heard about that. Significant.
It really is. Projections suggest data center power demand could double by 2026. That potentially makes it harder to transition away from fossil fuels if we're constantly needing more power for AI.
That's a side effect you don't always think about. And then there's bias, right? Algorithmic bias.
A major issue. AI systems learn from data, and if that data reflects existing societal biases, the AI will learn and often amplify those biases. Well, the infamous Google Photos tagging error years ago, or facial recognition systems being less accurate for certain demographic groups. There was also the Compass algorithm used in the U.S. justice system, which showed racial disparities in predicting recidivism risk.
So the AI isn't inherently biased, but it learns the biases in the data it's fed.
Precisely. And simply trying to achieve fairness through blindness, like hiding race from the algorithm, often doesn't work, because other data points can act as proxies. Defining and measuring fairness is actually really complex, with lots of conflicting mathematical models and philosophical viewpoints.
Different ways to be fair.
Right. Distributive fairness, representational fairness, procedural fairness. And adding to the problem, the field of AI engineering itself isn't always diverse, which can mean biases creep into the design phase too.
Okay, that's worrying. What about understanding how these AIs make decisions? Transparency.
Another huge challenge, especially with complex deep neural networks, they can be like black boxes,
Black boxes.
meaning data goes in, a decision comes out, but it can be incredibly difficult, sometimes impossible, to understand the exact reasoning steps the AI took to get there.
So you don't know why it made that decision.
Not easily. And sometimes the AI learned spurious correlations.
Yeah.
There were cases where an AI identified skin cancer better if the photo included a ruler, just because rulers were present in more training images of cancerous moles.
Whoa, that's not good.
No. Or another study where an AI wrongly concluded asthma patients have a lower risk of dying from pneumonia because they typically receive more intensive care, skewing the data. Lack of transparency makes it hard to catch and fix these kinds of errors.
I can see how that's a problem, especially in high-stakes areas like medicine or finance.
Absolutely. And beyond bias and transparency, there are broader societal risks. The potential for misuse by authoritarian regimes, for example.
How so?
Enhanced surveillance capabilities, spreading targeted propaganda or disinformation, digital warfare. AI tools could really amplify state control.
That's sobering. And then there's the really big one people talk about, existential risk.
Yeah, the long-term risk from potentially superintelligent AI. Figures like Stephen Hawking, Bill Gates, Elon Musk, even AI pioneers like Geoffrey Hinton and Yoshua Bengio have voiced concerns.
Concerns about what, specifically? Control, alignment.
A range of things. Yuval Noah Harari worries about AI hacking humanity by mastering language to manipulate beliefs and societies on a grand scale. Others worry about creating something far more intelligent than us that we can't control and whose goals might not align with human well-being. The alignment problem.
How do we ensure super smart AI wants what's good for us?
That's the multi-trillion-dollar question, isn't it? There are efforts in AI safety research exploring concepts like artificial moral agents or defining principles for developing beneficial machines. But it's incredibly challenging territory.
It sounds like it. Okay, so lots of risks. What's being done about them? Is there regulation?
It's definitely emerging. We're seeing a big uptick in AI-related laws being passed globally. Many countries have national AI strategies now.
International cooperation, too.
Yes, things like the Global Partnership on Artificial Intelligence, GPAI, and the AI Safety Summits, first in the UK in 2023, then Seoul in 2024. The Council of Europe recently agreed on the first international legally binding treaty specifically on AI. So governments are starting to grapple with this.
Alongside regulation, what about the open source movement in AI? Does that play a role?
A huge role. There's a very active open source AI community. Places like Hugging Face act as hubs. Companies like Google, Meta, Eleuther AI have released influential models or data sets.
So models are freely available.
Many powerful open-weight models are, yes, things like Meta's Llama models, Mistral Stable Diffusion for images. Researchers in smaller companies can download and build upon them, which spurs innovation.
But doesn't that also increase the risk of misuse if anyone can access them?
That's the double-edged sword, absolutely. It democratizes AI development, but also lowers the barrier for potentially harmful applications. Balancing openness with safety is a key debate. The UK's AI Safety Institute is even developing tools like Inspect to test the safety of these models.
Okay, so regulation, open source. It's a complex picture. Let's maybe step back again to the history. We talked about the winters, but where did AI start conceptually?
You can trace the theoretical roots back to Alan Turing in the 1930s and 40s with his theory of computation and the idea of an electronic brain.
The Turing machine.
Right. And his famous 1950 paper proposing the imitation game.
The Turing test.
Exactly. As a benchmark for machine intelligence, can a machine convince a human it's also human? Though its value as a true test of intelligence is debated now.
And the field itself, when did it get formally named?
That's usually credited to the Dartmouth Workshop in 1956. That's seen as the official birth of artificial intelligence as a research field. John McCarthy coined the term.
And those early researchers, they were pretty optimistic.
Incredibly optimistic. In the 60s and 70s, many believed artificial general intelligence, or AGI human-level intelligence, was just decades away. People like Herbert Simon predicted machines would be capable of doing any work a man can do within 20 years, back in 1965.
Wow. That obviously didn't happen.
Nope. Then came the reality check, the funding cuts.
Yep.
The first AI winter we discussed, followed by the expert system boom and bust, the second winter.
And now this current boom, starting in the late 2010s, really accelerating now with things like AlphaGo, GPT-3, ChatGPT.
Right, a massive resurgence of interest and capability.
It seems like there have always been different approaches within AI too, symbolic versus what?
Symbolic AI, sometimes called GUF-AI, good old-fashioned artificial intelligence, was dominant early on. It focuses on manipulating symbols according to explicit rules, like logic. It's good at high-level reasoning, planning, playing chess.
But not so good at
Things like perception, learning from messy data, common sense reasoning. That's where connectionist approaches like neural networks tend to shine. This connects back to Moravec's paradox and the physical symbol systems hypothesis, the idea that intelligence is symbol manipulation.
Was there a debate between these approaches?
Oh yeah, the neats versus scruffies. Neats favored formal logic and provable correctness. Scruffies were more willing to try messier, perhaps biologically inspired methods, even if they couldn't fully explain mathematically why they worked.
Neat versus scruffy, I like that. Are there other categories?
Well, there's the idea of soft computing, which embraces techniques tolerant of imprecision and uncertainty. Things like fuzzy logic, neural networks, evolutionary computation fall under this umbrella sometimes.
And the big distinction everyone talks about now, narrow versus general AI.
Right. Artificial narrow intelligence, ANI, is what we have today. AI that's superhuman at specific tasks, playing Go, translating languages, recognizing images, but can't generalize that intelligence to other domains.
Like AlphaGo can't write poetry.
Exactly. Artificial general intelligence, AGI, is the hypothetical goal. An AI with human-level cognitive abilities across the board, able to learn, reason, and adapt to virtually any task a human can.
And we're not there yet.
Definitely not. As we said, tasks easy for humans, perception, common sense, are often hard for AI, and vice versa. Donald Knuth had a great quote about AI succeeding in basically everything that requires thinking, but failing at most of what people and animals do without thinking.
That sums it up well. How might we get to AGI, theoretically?
Broadly, two main paths are discussed. One is simply scaling up more data, much more computational power, refining current techniques like deep learning. Maybe intelligence just emerges from scale.
Throw more resources at it.
Kind of. The other path is trying to better understand and reverse engineer the human brain, building artificial neural networks that more closely mimic biological structures and learning mechanisms.
Understand our own intelligence to replicate it.
Right. Though progress in neuroscience is also slow and complex.
Okay, let's talk philosophy for a second. Consciousness, sentience. Does AI research care about that?
Mostly. No. Mainstream AI is focused on building intelligent behavior and useful tools. Whether the AI is actually conscious or sentient like a human is usually seen as irrelevant to achieving those goals, and perhaps impossible to determine anyway.
The hard problem of consciousness.
Exactly, David Chalmers' term, the subjective experience of what it's like to be something. That's seen as separate from the easy problems of explaining behavior and function, which is what AI tackles.
So AI researchers aren't really trying to build conscious machines.
Not typically, though some philosophers and futurists debate it. There was even talk in the EU about potentially granting electronic personhood to highly advanced AI, but that faced strong pushback arguments that rights belong to humans, and AI lacks true autonomy or sentience.
Interesting distinction. Now, looking forward, There's the idea of exponential progress.
Yes, Ray Kurzweil talks about the law of accelerating returns. The idea that technological progress isn't linear, it's exponential. The rate of progress itself speeds up over time.
Meaning change happens faster and faster.
Right. Wait, why article uses a great analogy. Imagine bringing someone from 1750 to 2015. They'd be utterly overwhelmed, right? The jump would be incomprehensible.
Yeah, definitely.
Now imagine the jump from 2015 to, say, 2045 or 2060. If progress continues accelerating, it could be just as drastic, or even more so. We might be on the steep part of the curve.
The S-curve model. Slow start, rapid growth, then leveling off.
Exactly. Technology often follows that pattern. We had slow AI progress. Now maybe we're entering the rapid growth phase for AI.
Which could lead us from ANI.
To AGI, artificial general intelligence, human-level smarts.
And potentially beyond that.
That's the idea of ASI, artificial superintelligence, AI that vastly surpasses human intellect across essentially all domains.
Okay, AGI first. If we did achieve AGI, even just at human level, would it just be like another smart person?
Probably not. An AGI would likely have significant advantages over humans right away.
Like what?
Hardware advantages. Speed. Electronic circuits are way faster than electrochemical brain signals. Size and storage. Memory capacity could be enormous. Reliability and durability. No need for sleep. Less prone to error or physical damage.
Okay, faster, bigger memory runs 247.
And software advantages. Editability. You could fix bugs or improve its code directly. Upgradability. Easily add new skills or knowledge. And critically, collective capability.
Collective capability.
Imagine a network of AGIs instantly sharing knowledge and coordinating efforts globally. Humans collaborate, but much, much slower.
Right. A hive mind of human-level intellects.
Potentially, yes. Which leads to the idea that once AGI is achieved, the transition to ASI, artificial superintelligence, might happen incredibly quickly.
An intelligence explosion.
That's the term often used. An ADI could potentially improve its own intelligence recursively, leading to runaway advancement far beyond human levels in a short time.
And whether that superintelligence would be friendly or beneficial?
That brings us back to the alignment problem and the existential risks. It's the great unknown and arguably the most important question surrounding advanced AI.
Okay, wow. We've covered a lot. From early optimism and those AI winters,
Through expert systems, the LASP machines,
to the current deep learning boom, the incredible capabilities of models like GPT.
but also the persistent challenges, combinatorial explosion, common sense, knowledge acquisition.
And the critical issues: bias, transparency, privacy, environmental impact, potential misuse.
And that looming question of AGI and ASI, the exponential curve, and the profound uncertainty about the future.
It really feels like we're at a pivotal moment.
It certainly does. The pace of change right now is remarkable.
So to wrap this up, thinking about everything we've discussed, the history, the breakthroughs, the risks, the potential future, if you, the listener, had to pick one single aspect of AI development to watch most closely in the next few years, what would it be? Something to really keep an eye on. That's something to ponder. Thanks for joining us on this deep dive.